This is Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss about question bank on Module 2 Quantum Mechanics, Part B, long answer questions. So the first long answer question on quantum mechanics is compare a particle with a wave and discuss about dual nature of radiation. First, we need to discuss what is a particle and what is wave, and then we should discuss about what is dual nature of radiation. Okay. So first, what is a particle? Particle has mass m fixed. It has a definite mass m and is located at a definite point r and can move from one place to another place. Okay, so this is a particle and it gives energy when slowed down or stopped. When you stop, when a particle is moving with some velocity, when you stop that particle, it is going to dissipate some energy. So it is going to slow down and it is going to give energy in the form of radiation, heat. The particle is specified by mass, velocity, momentum and energy. And how are you going to discuss about this dynamics of the particle? The motion of a particle can be explained by Newton's second law of motion. F is equal to dp by dt. P is nothing but momentum. So P is momentum, which is product of mass into velocity. So so you can just write momentum as mass into velocity. So then d into mv by dt, so m is constant, so m into dv by dt, and dv by dt is nothing but the rate of change of velocity with time is acceleration, so mass into acceleration. So using Newton's second law of motion, we can study the dynamics of particles, how a particle is moving with some velocity in time. Okay, so so this is about a particle. It has some definite mass and it can be specified at a definite location, and it has some velocity and momentum. You can study this particle using Newton's laws of. So then what is a wave? How is it different from a particle? A wave is not located at a definite point r. Particle is located, you can locate a particle at a definite point, but wave is, you cannot locate a wave at a definite point, and instead it is spread over a relatively large region of space. Okay, so particle is this, but a wave is not like that. Wave is like this. Okay, so particle can be located at a definite point, but whereas a wave cannot be located at a definite point. Instead, it is spread in a relatively large region of space. A wave is nothing but a spread out of disturbance. Okay, so you cannot locate it at a definite point. Instead, it is spread in a region of space. And how are you going to specify a wave? A wave is specified by frequency, wavelength, velocity, amplitude and intensity. Okay, whereas a particle has a mass, velocity, momentum and energy. Here wave, frequency, wavelength, velocity, amplitude and intensity, and we can discuss the displacement of a wave and using y is equal to a sin omega t, where y is the displacement and a is the amplitude and omega is the angular frequency. Okay, so now we know what is a particle and what is a wave, and how can we specify a particle and how can we specify a wave. Now, what do you mean by dual nature of radiation? Okay, we know that radiation is nothing but heat and light. Okay, we treat light and heat. Okay, so light and heat are radiation here. So light is a radiation and heat is also a radiation. Okay, so what do you mean by the dual nature of radiation? Light is treated as a continuous wave to explain the phenomena of interference, diffraction and polarization. Okay, so to understand what is interference, for example, we are going to treat light as a wave. Okay, so to what is interference? Interference is nothing but a combination of two or three waves. Interference is superposition or combination of two or more waves. So this is interference. Okay, how do we understand the interference? To understand the interference, we are going to treat, suppose I have light. So light, if I am going to treat light as a wave to understand the interference, for example. Okay, so light, interference can be of two types: destructive interference and constructive interference. Constructive interference, suppose I have two light waves, for example. These are my two waves. These two waves can undergo constructive interference. That means if the two waves are in the same phase, if the two waves in same phase, two waves in phase, if the two waves are in phase, so wave 1 is like this, wave 2 is also exactly in the same phase, then they will undergo constructive interference and amplitude will increase and intensity will also increase. Suppose two waves are out of phase, not in phase, two waves are out of phase. When two waves are out, one wave is like this and another wave is like this. Then what will happen to the resultant superposition of these two waves? We are going to get very small amplitude and very small intensity. Okay, so to understand this kind of constructive and destructive interference, we need to treat the light as a wave. Okay, similarly, to understand diffraction or polarization, we are going to treat light as a wave. Okay, so we have treated light or radiation as a wave to understand these phenomena, for example, interference, diffraction and polarization. Okay, and the second one, light is treated as a beam of photons to explain photoelectric effect and Compton effect. To understand the photoelectric effect, we need to treat light as a set of energy particle. Okay, we are going to treat light as a set of energy particle. Each particle is going to have energy h nu. Okay, so to understand interference, diffraction, polarization, we are treating light as wave, and to understand this photoelectric effect and Compton effect, we are going to treat light as a beam of photons. Okay, so the particle nature, beam of photons, photon is set of particles. The particle nature and wave nature appear mutually exclusive. Okay, to explain any one of these phenomena, we are going to treat light as either a wave or a particle. Okay, so that is why we are saying that particle nature and wave nature are mutually exclusive, and neither of the modes can separately explain all the experimental fact. Okay, so we cannot fix that light is a wave. No, if you fix light as a wave, you cannot explain photoelectric effect. Or we are going to treat light as a particle. In that case, you cannot explain, you cannot understand interference. Okay, so we cannot treat light either as a wave or a particle. Instead, we are going to treat light as a wave sometimes to explain some of the phenomena, and we are going to treat light as a particle, set of particles to explain some other phenomena. Okay, so light exhibits both wave nature and particle nature, and this is called as wave particle duality or dual nature of radiation. Okay, so we discussed about what is a particle and what is a wave, and then we explained the dual nature of radiation. That means that radiation is nothing but light or heat. So radiation has to be treated as a wave to explain some phenomena. Radiation has to be treated as a set of particles to explain some other phenomena. So radiation is having two phenomena. It can behave like a wave or it can behave like a particle. This dual nature, two types of different behavior is called as dual nature, is called wave particle duality of radiation. Okay, then de Broglie explained that not only radiation has dual nature, but matter also has dual nature, and that is different. Okay, so this dual nature or wave particle duality is not only exhibited by radiation, but also this is exhibited by matter. So okay, both radiation and matter have exhibit this wave particle duality. So matter behaving like wave is hypothesized by de Broglie. So that is called de Broglie hypothesis. Okay. So the second question, enlist physical significance of wave function according to Schrodinger and Max Born interpretation. So we need to discuss about physical significance of wave function. Yeah. So before going to discuss about the physical significance, first we need to discuss about what is a wave function, right? So wave function is a quantity whose variations make up matter waves. called wave function, which is denoted by psi. Wave function is nothing but a quantity whose the variations of this wave function can tell us the matter waves associated with a particle. Okay, so that is what is called wave function, and it is denoted by psi. So this wave function is going to connect the particle nature and its associated wave nature. So if you can calculate the wave function psi, you can understand both its particle nature and wave nature. Wave functions are generally complex, both real and imaginary parts. So we are denoting psi as a plus ib, where I is real part and this ib is the imaginary part. Okay, so psi is a quantity whose variations will tell us about the matter waves associated with a particle, and this wave function is a complex quantity. It has both real and imaginary parts, and if you can calculate the wave function for a particular particle, you can know both its particle nature and its associated wave nature. So that is a wave function. So what is its physical significance, right? So physical significance of wave function is psi itself doesn't have any physical meaning, because psi is a complex quantity, a plus ib or x plus y, iy. So it has both real and imaginary parts. So by calculating psi itself, you cannot tell anything because it's a complex number. Instead, we are going to calculate the square of its absolute magnitude, that is mod psi square, which is x square plus y square. Okay. So mod psi square is a positive quantity and it is proportional to the probability of finding the particle. So as we discussed, psi is nothing but the quantity which tells us about the matter waves, right? So matter wave is nothing but a probability waves which will tell us about the probability of finding the particle at any location x, right? So by calculating this mod psi square, which is a positive quantity, we can tell the probability of finding the particle. And it is usually convenient to have mod psi square be equal to the probability density of finding the particle rather than merely proportional to p, as particle exists somewhere over time. So we are going to define, this is called as normalization or normalized wave function. Okay, so by calculating integral minus infinity to infinity, so it is volume, so we are going to take the integral in 3 dimensions. So because dv is dx, dy and dz. So integral minus infinity to infinity, minus infinity to minus infinity integrals, mod psi square dv must be equal to 1, because if we trap the particle inside the box and ask the probability of finding the particle at any position x, probability is this one, this one, this one, this one, this one, this one. So when we sum up all these probabilities, it must be equal to 1. That means that particle is somewhere inside the box. It is not escaped from this box, but it is somewhere inside the box. That means that probability, when you add up all the probabilities, it must be equal to 1. So this condition is called normalization condition, and it is also called as Schrodinger and Max-Born interpretation of wave function. Okay. So this is the physical significance of wave function, that psi itself doesn't have any physical meaning because it's a complex quantity. Instead, mod psi square is a positive quantity and it has a physical meaning that it will tell us about the probability of finding the particle at a position x. And if you sum up all these probabilities, this must be equal to 1. This is called as normalization condition or normalized wave function. Okay, coming to the third question, matter waves are new kind of waves. Justify this concept by discussing different properties of matter waves. Okay, so matter waves are actually probability waves. We know that matter waves are not light waves, matter waves are not sound waves, instead they are probability waves. That means that matter waves will tell us about the probability of finding the particle at any position x. Okay, so now so what are the different properties? We need to discuss the different properties of matter waves. So the first important property of matter wave is that lighter is the particle, smaller is the value of mass, greater is the wavelength associated with it. Okay, so therefore wave behavior is significant for microparticles, whereas wave associated with macro bodies can never be detected. Okay. That means that as per de Broglie hypothesis, lambda is equal to h by m into v. That means lambda is inversely proportional to mass. Okay, if for larger bodies, heavier object, m is more. If m is more, 1 by m is small and lambda is very small, you cannot detect such wavelength. That means you cannot say that there is a matter wave. I mean, heavier objects do not have matter waves associated with it. Microparticles, that means mass is less, so 1 by small value it will be big. Okay, suppose microparticles 1 micrometer size, for example, right? So 1 by 1 micrometer, 1 by 10 power minus 6 will be 10 power 6. Okay, so then lambda will be large. So for such wavelengths you can detect. Okay, so that is why these matter waves are associated with microparticles and they are not associated with macroparticles or heavier objects. It's very important, right? So matter waves are associated with only microparticles or angstrom atomic particles, not macroparticles. Okay, then we need to explain that lambda, as per de Broglie hypothesis, lambda is h by mv. M is the mass. So if microparticles, m is small, so lambda will be large and we can detect those wavelengths. That means there are matter waves. If m is more, heavier objects, 1 by m is small and you cannot detect such wavelengths, so matter waves are associated with only micro. The second property is that if velocity is 0, lambda is infinite. If velocity is 0 here, 1 by 0 is infinite. Means waves become indeterminate. This shows that matter waves are generated only when the particles are in motion. Velocity 0 means particles are rest. When particles are rest, you cannot detect the wavelength because it's in wavelength is infinite. So these matter waves are produced only when the particles are in motion. Okay, so these are two important properties of matter waves, and yeah, so this third one is same as the first one. Matter waves are produced by the motion of particles and independent of charge. That means matter waves are neither electromagnetic waves nor acoustic waves, but they are a new kind of waves. So matter waves are not light. Electromagnetic wave means light waves. Matter waves are not light waves, not sound. Acoustic means sound waves. They are a new kind of waves which are probability waves. Okay, so it can be shown that matter waves can travel faster than velocity of light. Okay, so by using these equations, we can show that matter waves travel with velocity plus velocity of matter waves is greater than the velocity of light. And no single phenomenon exhibits both particle nature and wave nature simultaneously. At a time, you cannot show that that particular phenomena exhibit both particle nature and wave nature. They are mutually exclusive. Okay, so that is about the matter waves and its properties. The fourth question, using Planck's and Einstein theory of radiation, show that the wavelength associated with an electron of mass m and kinetic energy E is given by h by square root 2 me. Okay, we are going to use this Planck's and Einstein theory to prove this lambda is equal to h by square root 2 me. Okay, so expression of wavelength associated with a material particle can be derived on the analogy of radiation as follows. Okay. Considering the Planck's theory of radiation, the energy of photon is given as E is equal to h nu. So E is equal to h into nu. Nu is frequency. Okay. So nu is frequency. I can write frequency in terms of lambda wavelength. So that is hc by lambda. So energy of a photon is hc by lambda. Okay, where c is velocity, lambda is wave. Now coming to the Einstein energy mass relation, Einstein energy mass relation says that E is equal to m into c square, mass into velocity of light square. Okay. So therefore both of them are for energy of the particle, so they must be equal. So equation 1 and equation 2 must be equal. So that means hc by lambda must be equal to m into c square. So c cancelled out here. If I want lambda, so h by m into c, that is for photon. Photon velocity of photon is velocity of light c. But if for a general particle, of particle with velocity v, for a general particle with velocity v, lambda will be h by m into v. Okay. So this is For a particle, for a general particle, velocity will be v instead of c. C is only velocity of photon, but general particle is having velocity v. So then I am going to replace c by v. So lambda will be h by m into v. So that is h by p. Okay. Now, so once I have this equation for lambda, which is lambda is equal to h by p. Now I am going to write this momentum in terms of kinetic energy, where in the equation kinetic energy, I am going to write this momentum in terms of kinetic energy to prove the relation of h by square root 2mv. Okay. So yeah, so now what I have is h by lambda is equal to h by p. Now I am going to write momentum p. Yeah, so kinetic energy I want. So kinetic energy is, we know the formula for kinetic energy. So I am defining kinetic energy, denoting it by E, which is half into m square, half into mv square. So I am going to multiply with m on both sides. So m into E will be half m square v square. So m I am going to take this side. So 2me is equal to m square v square, or p is equal to m into v. So this m square v square will be p square. So that will be p is equal to square root 2me. Okay, so I am going to substitute this p in this equation. Okay, so lambda is equal to h by p, but p is equal to square root 2me. So therefore lambda will be h by square root 2me, where E is kinetic energy. This E is kinetic energy. Okay, so using Planck's and Einstein relations, we have proved that the wavelength associated with this particle is lambda is equal to h by p, or we can write down this momentum in terms of kinetic energy. So lambda will be equal to h by square root 2me, where E is the kinetic energy. So let us go to the next question. Determine an expression for the wavelength associated with electron accelerated by a potential wave. So we need to determine an expression for wavelength for an electron which is accelerated by a potential wave. Okay. So now we know that the wavelength associated with the particle. So as per de Broglie hypothesis, electron is a charged particle. It must have some wavelength. So let me write like that. Okay. So de Broglie, as per de Broglie, lambda is equal to h by p. Okay. Now I am going to write kinetic energy in terms of momentum p in terms of kinetic energy. Just now we have derived it. So that is h by square root 2m into E. Okay. So now lambda is equal to 2m into E. So now we can write, now we are saying that we have taken electron. Okay. So for this question we should start with Planck's. As we derived, we should start with Planck's theory. As per Planck's theory, energy of a particle h nu, which is hc by lambda, equation 1. And as per Einstein, we know that energy of a particle is mc square. So equating these two, we will get lambda is equal to h by p. And I can write this momentum in terms of kinetic energy, which is lambda is equal to h by square root 2me, where E is kinetic energy. Now, if the particle is a charged particle, then I can write down the kinetic energy in terms of potential. Okay. So yeah, so in terms of potential. Okay. So when a charged particle is carrying charge q and accelerated by potential v, then the kinetic energy is given by E is equal to q into v. So then the de Broglie wave equation, wavelength, which is equal to lambda is h by square root 2m into E. So this kinetic energy is now defined as q into v. So that will be h by square root 2mq into v. Okay. For electron, okay, so up to here we need to prove, starting from Planck's theory and Einstein theory, equating those two energies, getting lambda is equal to h by p and writing momentum in terms of kinetic energy. Now we know that for electron, charge is this and mass is this. So substitute these values in this equation. Lambda is equal to h by square root 2 mqv, where m is given by 9.1 into 10 power minus 31 and q is given as 1.6 into 10 power minus 19. So when we substitute these values, we are going to get lambda as 12.26 by square root v angstroms. So this is for an electron. The wavelength, the de Broglie wavelength associated with electron that is experiencing potential V and having charge Q. So when we substitute these values for electron, we are going to simplify this equation into lambda is equal to 12.265 square root V angstroms. Okay. So the next question, explain the difference between matter wave and electromagnetic wave. Okay, so here are the differences between matter waves and electromagnetic waves. Matter waves are associated with moving particles, whereas electromagnetic waves are produced only by accelerated particles. Matter waves wavelength depends on the mass and its velocity, whereas electromagnetic waves wavelength depends on the energy of a photon. Matter waves can travel with velocity greater than the velocity of light. Electromagnetic waves travel with velocity of light c. Matter wave is not electromagnetic wave, whereas electromagnetic wave has both electric field and magnetic field perpendicular that oscillate perpendicular to each other. Matter wave require medium for propagation. Electromagnetic waves are produced only by accelerated charged particle. Okay, so these are some of the differences between matter waves and electromagnetic waves. So next question, describe Davison and Germer experiment with a neat diagram and explain how it established the proof of wave nature of electron. Okay. So Clinton Davison and Lester Germer in the USA and G.P. Thomson in England independently verified the existence of matter waves. So this is the experimental set of Davison and Germer. And in this experiment, you can clearly see that there is an electron gun. So the electron gun is connected to a voltmeter. Okay, so we can shoot the electron, and this is a target. T is a target. So here we are taking target as a crystal, nickel crystal here. And when the electrons are, by changing the potential, we can shoot the number of electrons. So when the electrons are shooted onto this nickel crystal, they are scattered in different directions. So here I have a scale S. Okay. So scale has, this rotating scale can tell me the scattering angle, and I can count the number of electrons that are scattered at every angle. So this is the experimental arrangement of Davison and Germer. So in their experiment, they have measured the scattering intensity as well as scattering angle, and they found that there is a minimum and maximum in the scattering intensity. Okay, so minimum is at 35 degrees and maximum is at around 50 degrees. Okay, now to understand why do we have maximum at 50 degrees, they have changed the voltage. Okay, by changing the voltage, they found that a bump started occurring at 44 volts and it gradually increases. So this bump is gradually increasing and becomes maximum at 54 volts. Okay, so this is where it became maximum. As we increase further, this bump slowly started disappearing and it completely disappeared around 68 volts. So by changing the voltage, they found that this maximum of 50 degrees is occurring at a voltage of 54. Okay, so they found the maximum scattering angle as well as the voltage at which we get this maximum scattering angle. So using this de Broglie wavelength relation, we can calculate lambda associated with this electron. So lambda is equal to h by square root 2 mqv. So this is E is the charge of electron, m is the mass of electron, and v is 54 volts. The potential, they found that 54 volts. So by substituting all these values, they found that the wavelength associated with the electrons is around 1.66 angstroms. Okay, now they have used nickel crystal. Okay, so the so as per Bragg's law, this condition must be satisfied for waves. If electrons behave as waves, this Bragg's equation, which is 2d sin theta equal to n lambda, must be satisfied. If electrons behave as a wave, there will be diffraction, and that as per diffraction, this condition must be satisfied. Okay, so using Bragg's equation, also they have calculated the calculated wavelength. So from this equation, you can calculate wavelength as 2d sin theta by n. Okay, so here there is only one first order, so we are going to take n as 1, and d is 0.91 for angstroms for nickel crystal. So they are taking nickel crystal. So For nickel crystal interplanar spacing, so the interplanar spacing is D, which is 0.91 angstrom, and theta, the diffraction angle, is 65 degrees. Okay, so this, where did we get this 65 degrees? Okay, using this crystal, you can see that this is where you have 54 volts. This is the angle of incidence, and if the electrons, if you treat electron as a wave, it is getting diffracted. Okay, so this is the scattering, incident beam and scattered beam. Okay, the maximum you are getting at 54, and the maximum scattering angle is 50 degrees. So if I draw a normal to this plane, this is the normal, and the total angle is 50 degrees. So 25 is here and 25 here, and this is the bending or diffraction, right? So if I want to calculate the diffraction, this normal must be 90 degrees. So already 90 minus 25, I get 65 degrees. So that is how I calculate the diffraction angle. Okay. So diffraction angle is 65 degrees. By substituting all this in this equation, Bragg's equation, I am going to calculate the wavelength, and the wavelength found out to be 1.65 angstrom. So as per de Broglie's wavelength, 1.66, and as per this Bragg's equation, we are getting the same wavelength. So both of them are matched. This means that as per de Broglie, these electrons, which are charged particles, are behaving like waves. That is the reason why we find the same wavelength, where in Bragg's law, we have treated electrons as waves. To explain diffraction, we must treat light or radiation as a wave. Here, we must treat electrons as set of a beam of electrons must behave as a wave. Okay. So the recent experiment proved that the value of wavelength of electron is found to be in good agreement with both an theory and experiment. That is, a beam of electrons behave like a wave. Okay, so Davison and Germer experiment proved that the existence of matter waves. Coming to the next question, considering dual nature of electron, derive Schrodinger's time-independent wave equation for the motion of an electron. Okay, we need to derive the Schrodinger time-independent wave equation. If a particle of mass m, so we are taking a particle of mass m, of electron of mass m moving with velocity v is associated with a waves, then psi must be a wave function of the particle. So if we are taking electron as a particle which is having mass m and velocity v, then it will behave like a wave. And to understand this wave nature, we are going to define a wave function psi. Okay. Now we do not know what kind of the form of matter wave, so we are going to assume that the wave function is this kind. Psi of x is equal to psi naught into sine omega t minus kx. Okay. So then we are going to differentiate this wave function twice, because in general the wave equation is a second order differential equation, right? So by differentiating this wave function, we are going to get this. Okay. So for example, yeah. So differentiating the wave function first, so what we'll get is dou psi by dou t will be psi naught cos omega t minus kx into minus k, and differentiating again dou square psi by dou x square will be psi naught, sine will be minus, so minus sine omega t minus kx into minus plus k square. So that is dou square psi by dou x square is equal to minus k square. Psi naught sine omega t minus kx is actually psi. So k square psi. So I can write this equation like this: dou square psi by dou x square plus k square into psi equal to 0. So that is how I got. So I differentiate this equation, wave function equation, twice, and I ended up with this equation 3, which is dou square psi by dou x square plus k square psi is equal to 0. Here k is propagation vector, which is equal to 2 pi by lambda. Okay, now I am going to substitute k, so dou square psi by dou x square plus k square into psi is equal to 0. K is equal to 2 pi by lambda, that means k square is equal to 4 pi square by lambda square. So I substitute this in this equation. Okay, so dou square psi by dou x square plus 4 pi square by lambda square into psi is equal to 0. So that is what I get. Okay. So now from de Broglie's equation, de Broglie's relation, the question is that using dual nature of electron. So using this dual nature of electron, we know the wavelength of associated with this electron is lambda is equal to h by mv. So I am going to substitute this equation here wherever lambda is there in this equation. I am going to substitute this equation here. Then I am going to end up with next equation. Okay. So I am going to get this equation because lambda is equal to h by mv. Okay. So 4 pi square by lambda square. So here h square m square v square will go to the numerator. So 4 pi square m square v square by h square into psi is equal to 0. Okay. Now I am defining a new quantity h cut, which is equal to h by 2 pi, where h cut square will be h square by 4 pi square. So I am rewriting this equation saying dou square psi by dou x square, 4 pi square by h square will be actually h cut square. So m square v square by h cut square into psi. Okay. Now, so I want the total energy of this particle is kinetic energy plus potential energy. This particle can experience some potential because it is a charged particle. So kinetic energy we know it is half mv square, but potential energy I do not know. So I am just assuming it is v. Okay. So from this equation I can write to So let me this equation. So E is equal to half mv square plus v. Okay. So this is potential energy. Now I am going to multiply with m on both sides. So me is equal to m square v square. This is velocity. M into v. So this is potential. Okay. So the m will go this side and m will also come here. Okay. So now m square v square will be equal to 2m E minus V, because I am going to take this side, this term. So E, it will be minus. So that will be m square V square equal to 2m into E minus V. So I am going to substitute this m square V square in this equation. Okay. So then it will become dou square psi by dou x square plus 2m into E minus V by h cut square into psi is equal to 0. Okay, so this is the time independent Schrodinger wave equation in one dimension. You can write this time independent Schrodinger wave equation in 3 dimensions. So dou square psi by dou x square plus dou square psi by dou y square plus z square into same, and where you can remove all these terms by a Laplacian del square, which is dou square by dou x square plus dou square by dou y square plus dou square by dou z square, which is called as Laplacian operator. Laplacian operator. Okay, so we have derived Schrodinger time independent Schrodinger wave equation in using de Broglie's wave particle duality for electron. Assuming that a particle of mass m is confined in a field or free region between impenetrable walls of infinite height x equals 0 and x equal to a, show that the energy levels of a particle are given by n square h square by 8m square, 8m a square. Okay, we are going to derive this equation for energies. Okay, as mentioned, I am defining a particle trapped in infinite potential well where potential is in 0 inside this well and is infinite at the boundary. So potential is defined here. V of x is equal to 0 in the well and it is infinite outside the well. So for such a particle which is trapped in infinite potential well, what are the energies? Okay. So we are going to solve the Schrodinger wave equation for this problem. So so this is the Schrodinger wave equation in 1 dimensions. Inside the well, we know that potential is 0. So when we substitute 0 in this equation, we get dou square psi by dou x square plus 2me by h cut square psi is equal to 0. And when you solve this second order differential equation, so which is dou square psi by dou x square plus k square psi. For example, if I define this as k into psi is equal to 0, so this is d square plus k square into psi is equal to 0, d square is equal to minus k square, or d is equal to plus or minus ik. So you can write the solution for this as psi of x is equal to, you can write psi of x is equal to a e power minus ikx plus b e power plus ikx minus ikx, or you can write psi of x as a sin kx plus b cos kx. Okay, by solving this second order differential equation. Okay, so now we do not know what are these unknown constants. We have the wave function, but unfortunately we have a and b. We do not know how to. We need to know these a and b. Once we know these a and b, we can write down the wave function. So to calculate the unknown constants, unknown constants. What are the unknown constants? A and B. To unknown the constant, we are going to use periodic boundary conditions. Periodic boundary conditions of wave functions. What do you mean by these periodic boundary conditions? Periodic boundary condition means that the wave function, whatever the wave function inside, the wave function must be 0 at x is equal to 0 and wave function must be 0 at x equal to a. Okay. So psi of x is 0 at x equal to 0 and psi of x is also 0 at x equal to a. So this is the first boundary condition and this is the second boundary condition. So we are going to apply first boundary condition and to this solution and see when x is equal to 0, psi of x is equal to 0. That means psi of x is 0, a sine k into x equals 0 plus b cos k into 0. So that means sine 0 and cos 0. Sine 0 is 0 and cos 0 is 1. So this means this is 1. So b into 1 equal to 0. That means b is equal to a. Applying second boundary condition, psi of x is equal to 0 at x equal to a. So 0 is equal to a sine k into a plus b cos k into a, but b is already 0. We have a sine k into a is equal to 0. So a sine k is equal to 0 means either a can be 0 or sine k a can be 0. We cannot take a is equal to 0 because a is equal to 0 and b is equal to 0. That means wave function is 0, which is not true. Okay. So that is why we are going to take sine k is equal to 0. Okay. So sine of x is equal to 0 for x is equal to n into pi. That means x is actually ka. Ka must be equal to n pi or k is equal to n pi by a. So we have calculated this constant k which is equal to n pi by a. But still we have this a hanging here, right? So to calculate this a, we are going to differentiate this equation twice. This psi of x we are going to differentiate by substituting what is the value of k. Okay, so differentiate this wave function twice. So first differentiation will be dou psi by dou x is equal to a cos n pi by a into x into n pi by a. Second differentiation will be dou square by dou x square minus a sine n pi by a into x is equal to n pi by a whole square. So that means n square. Okay, so a sine n pi by x is actually psi of x. So that is I have minus n square pi square by a square into psi of x. So when I can write this equation, from this equation I can write it as dou square psi by dou x square plus n square pi square by a square into psi is equal to 0. So this is what I am going to get when I substitute, when I differentiate the equation twice. Okay, let me show you that here. So by differentiating the equation twice, I am going to end up this here. Okay, so this is equation 6 and compare the equations 2 and 6. This is 6 and this is 2. Okay, so actually 3. Okay, so let me write here. So equation 3 is dou square psi by dou x square plus 2me by h cut square into psi is equal to 0. Equation 3. The equation 6 is dou square psi by dou x square plus n square pi square by a square into psi is equal to 0. 6. So these two equations are second order differential equations except the free factors, they must be same, except these free factors, so they also must be same. So equating these two, 2me by h cut square must be equal to n square pi square by a square. We have calculated the energies, which is equal to n square pi square by h into h cut square by 2me square, or you can substitute h cut square is equal to h square by 4 pi square. So by substituting that, we'll get n square pi square h square by 4 pi square. So that will be 8m a square and pi square will cancel out. We get this equation. So these are the energies associated with a particle that is trapped in an infinite potential well of width 0, width a. Okay. So n square h square by 8m a square. So the last question is that discuss the results from the eigenvalues, eigenfunctions and probability density for a particle in a one-dimensional potential box of infinite height. Also sketch the figures. Okay. So we have already done this particle trapped in an infinite potential box, except that here they are asking us to calculate eigenvalues and eigenfunctions, right? So eigenvalues are nothing but the energies. Eigenvalues are nothing but energies. Just now we have derived energies. En is equal to n square h square by 8m square. So now we have to calculate eigenfunctions, which are wave functions. So eigenfunctions are nothing but the wave functions. Okay, so let me write here. Eigenfunctions are nothing but wave functions. Eigenvalues are nothing but energies. En and psi n. So we need to calculate En and psi n, and also we need to find out the probability density for a particle in the one-dimensional box and sketch the figure. So we need to calculate what is mod psi square. We need to plot these figures. Okay, fine. First, again, we have to repeat this particle trapped in infinite potential well. Okay, so we have done all the derivation, solving one-dimensional, storing a wave equation in potential well. Potential well is V, potential is 0 inside the well. So substitute V is equal to 0. We are going to get the second order differential equation. The solution of the second order differential equation is psi. And then to find out these unknown constants A and B, we are going to use the boundary conditions of the wave function. And then using these boundary conditions, we found out that B is equal to 0 and K is equal to n pi by A. And so finally we get psi of x is equal to A sine n pi by A into x. So to find out A, our energies, we are going to differentiate this equation, say equation 5 twice, and when we differentiate this equation twice, we get this equation 6. Comparing equation 6 and 3, we get the energies, En. So these are called eigenvalues. Energies are nothing but the eigenvalues. Next, we calculate eigenfunctions with other wave functions. So to find out this unknown constant A in the wave function, we already have the wave function psi of x, but there is still one unknown constant A. So we need to find out this unknown constant A. So that we are going to use normalization condition of the wave function in the given region 0 to A mod psi square dx equal to 1. Okay. So mod psi of x is given as A sine n pi by A into x. Okay. So mod psi of x square will be A square sine square n pi by A into x. Okay. So that is what I have substituted here. I am rewriting the sine square as sine square x is equal to 1 minus cos 2x by 2. Okay, 1 minus cos 2 into x. So this is x, 2x into, so there is a 2 here. Okay, by 2 into dx equal to 1. So mod psi square x dx must be equal to 1 as per normalization condition. Right. So here, so by rewriting this equation, sine square as 1 minus cos 2x by 2. So I am separating out the integral. So this is a square integral 0 to a. This is dx, and this is again integral cos 2 n pi by a into x dx. These two integrals must be equal to 1. Okay. So first integration will give us x, and second integral will give this. So with the limit 0 to a. Okay. So when we substitute the limit x is equal to a and minus 0, but here the sign, when we substitute x in the place of x, we substitute a will cancel out, we will get sine 2 n pi, which is 0. And again, if we substitute the lower limit, sine 0 is again 0. Okay. So this second term will all go, what we left it is the only first term. So a square by 2 into a is equal to 0. So a will be square root 2 by a. So when we substitute this a in the equation, a sine 2 pi n pi by a into x, so we get this eigenfunctions, square root 2 by a into sine n pi by a into x. So we have calculated eigenvalues which are energies, and eigenfunctions which are wave functions. And now we have also plotted the probability of finding the particle, mod psi square. So this is psi of x in different energy levels, first energy level, second energy level, and third energy level. We have also plotted mod psi square, which is probability of finding the particle inside this box. So this is the box. So x is equal to 0. I'm sorry. So this is x equal to a. So inside the box, this psi of x is equal to mod psi square of x. Psi square 1 will give us a probability of finding the particle in the first energy level. Psi square 2, mod psi square 2, that is this green, will tell us the probability of finding the particle in the second energy level. And the blue one is in the third energy level. Okay, because it is mod psi square, we always have positive values, whereas here in the wave function we can have both positive and. So we have answered this question that we have calculated the eigenvalues and eigenfunctions and probability density of particle, and we have also sketched the figures. Okay. So these are some textbooks I have used in the presentation, references books, and summarize. I have discussed the longer answer questions on quantum mechanics in this presentation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.